and detect that.
Hey everybody, it's time for This Week in Science and Education. This is episode 91, How Vegetative State Patients Communicate. Hi everybody, this is Kevin Kugler from the Virtual Researcher On Call program. Thank you for joining us today on This Week in Science and Education. Really interesting show today. How do patients in a vegetative state communicate? Well, we're going to find out. We're going to talk to Dr. Adrian Owen from the University of Western Ontario. But before we do that, just want to say welcome again to Thomas and Colin. It's Colin Jago from the Pine Ridge District School Board. Hi, Colin. And Dr. Thomas Merritt out of Laurentian University. Welcome, gentlemen, and good to see you again. It's been a month or so since I was here. So
good morning.
Thanks for rolling without me, but good to be back with you guys. So I'm looking forward to the show today. Let's go right to our guest, Dr. Adrian Owen, is from the University of Western Ontario. And Dr. Owen, first of all, thank you for taking the time to chat with us today. This is, I told you before the show that I've been looking forward to this for weeks, and it's absolutely true. Your research has been a hot topic in so many media outlets the last, well, at least the last 2 years that I've been aware of it, but of course it goes beyond that. Perhaps you could start by just telling us a little bit about who you are, what you do, and why it's important.
Sure. Well, it's a great pleasure to be here. Thanks for inviting me on. I work with patients who have had extremely severe brain injuries, and those are usually one of two types, either what we call a traumatic brain injury, sporting accident, or more often a vehicle accident, been in a car that's been in a collision, or what we call non-traumatic brain injuries. These typically happen in older people and would be things like when the brain has been starved of oxygen for a period of time, perhaps during a cardiac arrest. We see quite a lot of patients who have been involved in near drowning incidents. The thing that these people all have in common is that they end up in a so-called vegetative state. And this is a really, really unusual and troubling condition, because the patients are awake. They wake up, they open their eyes, they often appear to look around the room, but they have no awareness, or they appear to have no awareness of anything going on around them. So you can't attract their attention. If you ask them to look over here, nothing happens. If you call their name, nothing happens. So they're in this very strange halfway situation when they're neither here nor there. They're awake and they're animate, but they don't seem to be in touch with the world. And what we've been doing, actually, it's taken almost 15 years to get this right, but is working on types of brain imaging, specifically MRI, magnetic resonance imaging, using that to actually show that some of these patients aren't what they appear to be. If you get into their brains and image their brains, we can see that some of them are actually conscious, even though they appear not to be responsive. They can actually respond with their brains. And also, as you've already alluded to, some of them can even communicate with the outside world using fairly complicated types of what we call a brain-computer interface using MRI. So that's what I do. I develop those sorts of techniques, and I go out and I look for patients who really aren't what they appear to be. They appear to be in a vegetative state, and it turns out they're in some other condition that we might call a locked-in state, where they can't physically respond with their bodies, but they're still nevertheless aware inside, if you like.
So, I was listening to some of your other interviews earlier, and the idea of the vegetative state is something you really have to explain, and I think you've done a nice job of that. It's not a coma, although I think you said that people who come out of comas can end up in a vegetative state. There's apparently a disconnect. So, I mean, the example on one of the interviews I was listening to this morning, you had an individual where you had him imagine tennis, and then you asked him questions, and then he could control his brain so that the imaging would give you an answer to questions that you were putting forward. But the same individual was not able to physically respond. So, where is the disconnect? And I mean, I guess at some level we would have to define what is a response, but how is it that you can have these sort of complex pattern signaling in the brain, and the individual or any of the individuals that you're working with can't turn their head and respond or nod or wink or, in some way, more traditional way, communicate with us?
Yeah, that's a really interesting question because, and we don't really have an exact answer because, of course, we've only known that these people exist for a few years, because up until a few years ago, all these people would just go unnoticed because clinically, doctors rely absolutely on physical responses to know whether somebody is conscious. Think about, I'm sure everybody's seen some sort of medical drama on TV when the doctor's at an accident, sitting beside the road and says, "Squeeze my hand if you can hear me." The doctor's not really interested in hearing. He or she is interested in getting a response out of the participant, because that indicates that the person is conscious and they are aware. They know that they're being asked to do something and they can do it. And that really neatly illustrates, I think, how until recently we've been absolutely reliant on physical responses to assess consciousness or awareness. Now, what we've done with the brain imaging is we've come into this scenario and said, well, hey, what if some of them couldn't actually respond? Physically, that is. Let's see whether we can just look at their brains and find out. So right now we're at the stage where it turns out that that's true. Some people can only respond with their brains. But why it is exactly, we don't know. I've got a few ideas. If you think about how movement is organized in the brain, what we have the motor cortex, and the motor cortex allows me to do this stuff, right? To actually move my arm. Or squeeze a hand, to use the example I've used previously. Now, the premotor cortex, the area in front of the motor cortex, is right up here. That sends a signal to the motor cortex to sort of prepare to move, to get everything organized to make that movement. And what we're seeing in these patients is their premotor cortex is absolutely fine. Their premotor cortex is sending that signal to prepare to move. But it's not getting beyond there. The motor cortex is not actually initiating the action. And it turns out that our scanners are sensitive enough to be able to pick up the intention to move. So the patient doesn't have to actually move. We're kind of sneaking in under the wire and picking up the intention to move.
So if that's true, sorry, Colin, if that's true, can you predict based on what regions of the brain have been injured as to...
Yeah, that was my question too.
Sorry, I'll let you take the question.
No, that's okay.
No, I wasn't going to let you anyway. Can you predict, that this individual is likely to fall into this category or that category based on the state of the brain?
So partly, unfortunately it's not absolute. I wish we could, and the reason is very simple. It's because all of these patients come from different scenarios. So one guy, may have run into a telegraph pole while not wearing a seatbelt, and he's hit the windscreen of his car. The next person may have spent 2.5 minutes underwater, nearly drowning. Right now, the brains of those two people are going to look completely different because of the nature of the injury. But the net effect is the same.
Okay.
That they end up in a vegetative state.
Right.
Colin, do you want to ask something, or can I just interrupt you again?
No, go ahead. I'm formulating my next one because that actually answered the next question I was going to ask too. So that's good. You're anticipating my needs, so that's wonderful.
I'm reading your mind.
I know.
So, one of the things that has changed drastically since I was a student in the 80s is our appreciation of how much the brain can actually heal. So I remember in basic biology being told that brain tissue does not heal, neural tissue does not heal. When you have an injury, that's it. And there was work done in the late 80s, I think, on canaries and birdsong, and they were showing that the regions of the brain that were involved with birdsong expand and contract through time, and that's growth and loss of nerve cells. And people realized, oh well, if that can happen in canaries, then this is going to happen elsewhere. So, how much of the difference from individual to individual could be the injury, or could be the way that individual is able to respond or heal to an injury?
That's very true too, and of course that's complicated by the fact that we don't see everybody immediately after their injury. Some of these people we see, in fact, the gentleman you were referring to previously, I think it had been 12 years since his injury. So these patients aren't on life support machines typically. We're not keeping them alive. They obviously have to be fed artificially, but their heart pumps normally. They breathe normally, so they can survive for many years. And typically they will, unless they have an infection or something else that kills them. So you're absolutely right that when we come to see these patients, we really have no idea often how much is exactly the result of the injury and what has happened since then. Now, one way we're getting at that now is we're starting a longitudinal study where we follow patients, and we've just started to do some of these techniques in patients who actually are on life support machines. These people are still in the ICU. They may have had a vehicle accident 5 or 6 days ago. We're putting them in the scanner for the first time, looking at their brains early on, and then following them every few months with repeated scans to try and answer the question you've just given me.
So, sorry, Thomas, I got to jump in here for a second, just to give Dr. Owen somebody else to look at for a change. So here's what I can't rectify in my own mind here, Dr. Owen, is that, I'm going to use Thomas as an example. Okay, so Thomas is an active rower, right? So he's very, he's physical. He has that type of lifestyle, right? He's always on the move, always on the go. For somebody like Thomas to lay there in emergency room for 1 day, 2 days, 5 days, 10 days, years, not be able to communicate with anybody, like what's the mental state that we're now dealing with some of these patients? It's mind-boggling. Have some of them gone mad? Do we have any way of identifying, what their mental state is? I can't imagine, what this is like for them day after day.
Mm-hmm.
One of the most interesting things I've found about working in this area is that I'm constantly surprised by what I found. So 10 years ago, I wouldn't have believed this situation was possible, that a patient could be entirely conscious and even able to communicate yes and no responses by changing their brain activity, yet entirely physically non-responsive, lying completely in a non-responsive state. And to address your question directly, another thing that I think is very surprising is that these patients are not necessarily in the emotional state, if you like, that we may all think they are. And I guess the best way to say that is, you don't know what this is like until you're actually in the situation. I think for most people, this sounds like it would absolutely be the nightmare scenario. The only data that we have on this is from a study in Europe of a large group of so-called locked-in syndrome patients. Now, these are patients who are not completely locked into their body, but they can typically move an eye or blink an eye or move an eyebrow to communicate, but their day-to-day situation is rather similar. They can't do anything for themselves. They can't move. Now, those patients, a study came out last year showing that those patients actually aren't generally depressed. They aren't generally wanting to die. They would prefer to go on living. Obviously, they're not happy with this situation, but they certainly aren't in the situation that I think we all would assume we would be if we were in that situation. And I think this is very important. One of the things the reason why we're really pushing the technology so hard to allow us to communicate with more of these patients is that the best way to find out what state somebody's in is to ask them. And if we can ask them, they can report it, because I think we may have been making a lot of assumptions over the years about these patients and their desire to live or die, or whether they're in pain or not in pain. And a lot of that stuff may turn out to not be as simple as we think it is.
Mm-hmm. Okay, along that lines, I have if you're asking for a response, and now, I grant that this is early, and you're using fMRI and brain scanning. I've done some reading in the past of things that are maybe other ways of communicating that may not be quite so scientific, facilitated communication, some of those kind of things. What are the checks and balances with your hypothesis? Like you say, a person can indicate yes or no on a consistent basis. So what's different about what you do with the scans that leads you to think you're on the right track versus some other ideas and techniques?
Yeah. Well, it's interesting. It's an interesting question. Obviously, it's the sort of thing we have to tackle with reviewers of our scientific papers. So what I will say is that what we do, in a sense, is extremely conservative. There is no possibility that a patient could generate a yes response with the fMRI, and for that not to be true. The reverse is often true, and I can come to that in a minute, that we can get no response and have no idea why that's happening. But I'll tell you the reason why. So what I do specifically with the fMRI is I ask people to imagine doing something. It's typically to imagine waving their arm around as if they were playing a game of tennis. And that's to convey a yes response. And this is because when you imagine moving your arm like that, it produces activity in the premotor cortex, the part of the brain that sends the signal to the motor cortex. But it's not just something that happens at a moment in time. What we do is we put the patient in the scanner. I'll say, I'm going to ask you to imagine playing tennis. And whenever you hear the word tennis, start doing it. And when you hear the word relax, stop. And what we do is we do this for 5 minutes continually. We say, tennis, stop, tennis, stop. And typically we leave them imagining playing tennis for 30 seconds at a time. And then the only way I would conclude that they were doing this is if I saw activity in the brain shoot up when I said tennis and continue like that for 30 seconds and then come down when I said relax, and then stay down for another 30 seconds and then shoot up again. The best analogy is to get a statistically significant result, the person has to have done the equivalent of raise your left arm, put your left arm down, raise your left arm, put your left arm down 10 times over. It is simply impossible that this could happen by chance. Okay. And I think that's something that's often not conveyed well when you just see the single static image of a brain activity and I'm saying yes, you're saying yes. Yeah. And the other the other aspect of the checks and balances, of course, the way we tested this procedure, the way we, if you like, prove that it works is that we started off by asking patients questions that we didn't know the answer to. It was a totally blinded experiment. So in the first paper we showed this in 2010, the family gave us a whole list of names of relatives and places the guy had been to, and we decoded all this. Now, I had no way of knowing that the last international destination he'd been to was the United States prior to his accident 5 years earlier. But we did decode that from his brain, and there's no way I could have known that unless he was conveying it.
Fascinating.
So that may answer my next question is, when you do these yes-no answers, there are lots of relatively simple organisms that can do yes-no responses that we don't really attribute full consciousness to. So how do you extrapolate from that yes-no to full consciousness? And perhaps that is what you were just describing, where you can get more complicated things than just imagine a game of tennis.
Absolutely. I mean, at least at the moment, we don't do much that's more complicated than getting somebody to imagine that and imagine it for a yes and imagine something else for a no. But what we then do, it's a bit like 20 questions, where we ask a systematic series of yes and no questions to get towards answering whether, how conscious the person is and what does it mean to have that sort of consciousness. Right. So one obvious thing is, do they know who they are? Well, you can do that with a yes/no. Do they know where they are? We say, are you in a hospital? Are you in a supermarket? What year is it? We had a patient recently who reported that it was 2013, despite the fact that it was 15 years since his injury. I mean, wow. It's reasonable to believe he might still think it was 1998. We go through this series of questions, and I guess we took it to its real conclusion, I think, in a paper that just came out this year, where we showed that a patient could solve really complicated problems. We gave him difficult reasoning problems using a very standard test of intelligence. It's often used to test general intelligence. It's a reasoning test that requires a lot of thinking through various scenarios. But it's a test that you can deliver the answers as a simple yes or no. So we gave him the problems, and then we said, when you're ready, either imagine playing tennis for this response, or imagine moving around your house for that response. And two things came out of that study that are very interesting. One is this guy could do complex reasoning, and if he could do that, he's not only conscious, he's conscious like I'm conscious, because I have trouble with these tests. But also, we were able to assess how good he was at reasoning, because once we made the problems harder and harder, just as you and I would, he started to give us the wrong answers. And it wasn't that he started to give random answers, he started to give the wrong. He said no when it was a yes, and yes when it was no. So we could actually map how good his problem-solving ability was, which was really fascinating. And the guy had not moved a muscle in years.
Wow.
Okay. Sorry, Colin. I have a moment. I have a student moment here. Okay. This is for the students who are considering research as a career choice. So a lot of researchers, you guys will back me up on this. You could go years. Some could go their entire career without having what you had, which is the aha moment. Okay. Describe for those students who are thinking about this, research as a career choice, the moment where you went, oh my God, I'm communicating with somebody that no one thought, would ever be possible. Where were you? What did you feel? What was the reaction? What was the room like?
I have to tell you, this still happens to me, even though it was 2006 that we had the first aha moment when we established that a patient who, not moved for a few months was actually conscious, and that, really was a eureka moment. It still happens to me every time I find one of these patients. I still find it absolutely astounding that this can occur and that these patients can generate these brain states and that we can detect them, and the technology is at the stage where we can do this. I still find it astonishing, and in many ways that's what drives me to continue doing this stuff, because it's
Wow.
extremely rewarding and motivating, because it's an exciting combination of medicine and technology and computers and mind reading, and it's got really a lot going for it as far as keeping me interested and entertained. The first time it happened was in 2006, and part of the reason why it was so exciting, I think, is that by that stage we'd been working towards it since '98. So we've been working on this problem for 8 years, and each year we scanned a few patients and found a few interesting patterns of brain activity, and we just couldn't nail exactly what they meant. We'd play a patient a bit of speech, or we'd show them a face of somebody they knew, and we'd see patterns of activity in the brain that looked familiar and looked like the patterns that we thought we should see in a conscious person, but we couldn't really nail it. And the 2006 moment when, I first said to a patient, well, imagine you're playing a game of tennis and do this, and this entirely non-responsive person suddenly generated activity in their brain. I mean, that was indescribably amazing, and a really exciting moment for us doing the science, I think.
Thank you. Sorry, Colin.
I can't even imagine. I'm thinking one of the things we do in education a lot is talk about learning, right? And talk about how the brain learns and how children learns. And one of the biggest questions is, where does consciousness arise from? And so you're dealing with sort of that body control part of the brain and this ethereal thing called consciousness. And I'm just wondering your sort of take on that question, that where does consciousness arise from in humans based on what you see and what you research?
I'm glad you've asked me an easy question at last. So this is the big question.
Yeah, absolutely.
It's a hard problem. What is consciousness? Yeah. Where does consciousness come from?
For sure.
And I'm going to duck the question, right? And the reason, but I'm going to explain why I'm going to duck the question. And it's because I think a lot of people take what I would call a top-down view of consciousness in order to answer the question that you're asking me. They say, well, let's try and work out what consciousness is, right?
Right.
And a lot of people have been doing this for a few thousand years, in fact, and we've made some progress, but clearly we still don't know. And the approach my team takes is the complete opposite of that. It's to try and build up a model of consciousness from the basic building blocks that we know exist in the brain. Because, I'm not sure that trying to work out in a sort of a big philosophical way what consciousness is going to help us find consciousness in the brain, because there's not a consciousness node in there. There's not a little bit that we know does consciousness. It's some kind of property. Exactly. There is no switch. It's something that comes out of us having this complex brain. So what we're doing is trying to build up the things that are necessary for consciousness. And we're doing that in a series of ways. One is by looking at patients who have brain damage to particular areas of the brain, and that allows us to rule out some things and say, well, this guy's still conscious and he's lost his cerebellum, so obviously the cerebellum isn't necessary for consciousness. Right. The other way is we do studies with anesthesia, by giving doses of heavy sedation to healthy participants, people who volunteer to help us with the science, to look at how cognition changes as you gradually reduce consciousness, because that's a very controlled situation. If you administer an anesthetic agent, the person gradually starts to become unconscious, and we can measure what's going on in their brain at those times and work out, again, which things are necessary for consciousness and which things sort of just come in for free and have nothing to do with consciousness at all. We're also doing sleep studies. We have a sleep lab here at Western, and we put healthy participants in the lab. We tell them to go to sleep, and then we do EEG or electroencephalography on their brain to find out what happens when they're at different stages of sleep. And all of those things are to try and build up what consciousness is based on what we know that the brain can actually do. Right. And I think that even 5 years from now, we'll be in a much better situation to answer that question, to be able to tell you what consciousness is and what consciousness isn't. And I actually think, I believe that's being much more fruitful than kind of trying to describe it at a broad philosophical level, because if you do that, we've all got different opinions about what consciousness is. And some of them, are simply impossible because we don't have the mechanisms in our brain to support that sort of thing. So there you go. That's my long-winded and a roundabout answer.
That's a good answer, though. That's a good answer. Thank you.
Go ahead, Thomas. We both interrupted you for the last.
No, that's cool. I'm sure we're running out of time, but I had two things that I wanted to say. One was a comment based on your aha moment. A lot of times when we're talking to scientists, the breakthroughs that come through that we know about are a change in technology allows this, that, or the other. And the true breakthroughs are always a combination of technology and somebody with a clever idea. And I think that the nice thing about your example is you didn't say to us, well, we changed the imaging technology that was available, or the technology available changed. I thought of a really simple question to ask that we hadn't been asking, and that's what ended up driving this. And it's a really important point to get across to students. Everything isn't about the technology. It's often about how clever you are with the questions. And you are a very bright man, but you're also a very well prepared man. And those three things had to come together. You had to have the right technology, you had to have the right background, and you had to be willing to ask interesting questions. And that's what students can get out of the way we do science. So thank you for a really great example of a breakthrough moment that was it was up here. It was the way that you were working with what you had. The question that I had for you is another short answer. As you talk about building up of consciousness, the description that you seem to be supplying implies to me that, in fact, machines will become conscious in a relatively short period of time. So would you agree or disagree with that statement?
Well, I tell you, what I think is that machines will be able to emulate consciousness almost perfectly in a very short period of time. Whether they will actually be conscious or not is something that at that stage I'll hand over to the philosophers. I think we have machines right now that can give the impression that they're conscious, but I think most of us agree that, our PC isn't actually conscious, even though it can answer questions and it can tell us all sorts of information about the world. I think that's only going to get better and better. That's obvious. And I think there's going to come a time when you're not going to be able to tell the difference between a machine and a human. And at that stage, I still don't believe that, personally, that machine is going to be conscious. But, a lot of philosophers spend a lot of time wondering, well, if it perfectly emulates consciousness, doesn't that make it conscious?
Fair enough. I'll take that as an answer. So we still don't know whether Hal is going to dream when we turn the computer off.
That's right.
All
That's the looks like a duck problem, right?
Yeah. Gentlemen, I told Dr. Owen we'd be 20 minutes, and we're closing in on 35 or so. But Dr. Owen, if you don't mind, I have one more question for you, and then I promise we will let you go. And I'm going to reserve the right for the last question this time. Sorry, gentlemen. What is the ultimate goal with this research? Is the ultimate goal that we're going to find a way for these patients to be able to communicate, formulate sentences, and be able to communicate with their loved ones? Is that your ultimate goal with this research, or is your goal a little slightly different than to start to bring in other researchers to eventually achieve that end result or that end wish result? Talk a little bit about where this is going, and if you can, projected timelines next year. Probably a little too soon, but. What are your thoughts?
It's interesting. It raises another question about the way I see science, or the progress of science. I've never really had a big vision for where this is going to end up. Okay, I kind of follow my nose. I look for the next interesting question. I do what intrigues me. So really, I typically only look 1 or 2 years ahead. So right now, my immediate goal is the one that you started your question with. I would really like to perfect a so-called brain-computer interface. Some technique, it won't be based on MRI because that's simply too expensive and it's not portable. It'll probably be based on EEG or something similar. A technique that's portable, relatively inexpensive, in the tens of thousands of dollars range, probably, that a patient could actually take home with them and communicate on a daily basis with their relative. I mean, right now, the patient has to be in the scanner, and they can basically only answer the questions that we give them. So you're right, that device should be able to allow them to spell out words and actually initiate conversations for themselves. Now that, I'm absolutely sure, is something that's going to happen within the next 2 or 3 years. And that's because there's a lot of really smart people working on this problem. Either the gaming industry has a lot of interest in people using brain-computer interfaces to play computer games. It's not all about medical applications. There's a lot of really very clever people working on so-called brain-computer interfaces, and we're tapping into that technology to try and find ways of applying this to our patients. So it does require a perfect storm of us getting the right technology and the right patient becoming available at the right time, and so on and so forth. That's why it's not going to happen tomorrow. But the nuts and bolts are basically all in place, and I think we're going to see that in the next couple of years, and that's pretty exciting. The bigger goal, really, and it's related to the same thing, is to provide these patients with what we call autonomy. I think all we're really trying to do is to give them back a voice that they've lost, because the way it looks right now is many of these patients can make their own decisions and do have opinions about what should happen to them and do have emotions and feelings. And in a sense, we're trying to open the box to put at least a partial end to the situation where other people have to make every decision for them, from switching on a light or turning down the radio to whether they live or die. If we can give back some of that control to some of these patients by any means, I think that's really that's the big goal we've got here.
Well, Dr. Owen, I'm sure we're going to continue to follow your career and your research with interest, and 3 years from now, we're going to have you back on the show, and we're going to ask you how it's going, so be prepared
It'll
for
be a
that.
pleasure. Thanks very much for having me on.
Thank you so much for your time.
Thank you.
I know I speak for Colin and Thomas as well when I say that this has been absolutely fascinating. We'd love to spend hours and hours with you, but we'd rather you were in the lab helping those patients. So thank you so much for your time, and we'll look forward to seeing you again soon. Thanks, everybody, for another great episode of This Week in Science and Education. We hope you enjoyed it. And Dr. Adrian Owen is from the University of Western Ontario. You can find out more about his research just by Googling Dr. Owen at the University of Western Ontario. All sorts of fascinating stuff. I know we all did. And thanks, Colin. Thanks, Thomas, for another fun show. That was really great. Have a great week, everybody.